we're living through a revolution. Machines are learning to see, hear, and understand, not by following rigid rules, but by discovering patterns in oceans of data. Deep learning powers the voice assistants in our pockets, the medical software that spots tumors, and the self-driving cars on our streets. Unlike past tools, deep learning extends our intuition and perception, letting machines interpret images, music, and language. It's not about programming every step, but about systems learning their own rules from vast information. This shift is transforming science, business, and daily life, personalizing feeds, translating languages, and decoding genomes. Understanding deep learning is essential for anyone curious about the forces shaping our world. Let's explore how machines learn to think, inspired by the human brain, and demystify the engine of modern AI. Traditional machine learning required humans to handcraft rules, like telling a computer to find 4 wheels to spot a car. But this approach breaks down with new shapes or perspectives. You'd need endless rules for every variation. Deep learning flips the script. You show the model thousands of labeled images and it learns the features itself. It starts with simple patterns, edges, colors, then builds up to complex concepts like wheels and grills. The key difference? Deep learning extracts features automatically, learning from raw data. This makes it flexible and powerful, able to adapt to new data without constant human guidance. It's the leap from following a checklist to truly understanding what makes a car or anything else unique. That's why deep learning is at the heart of today's AI breakthroughs. At the core of deep learning is the artificial neural network, inspired by the brain's web of neurons. Data enters through the input layer, passes through hidden layers, and emerges as a prediction at the output. Each connection has a weight, like a volume knob, adjusted during training to improve accuracy. Neurons also have biases, thresholds that must be overcome to activate. Activation functions add nonlinearity, letting networks learn complex patterns, not just straight lines. Training uses backpropagation. The network compares its guess to the truth, then tweaks its weights to reduce errors. Through thousands of cycles, the network fine-tunes itself, becoming an expert at its task. This self-improving process is what gives deep learning its remarkable power. Neural networks have existed for decades, but 3 forces finally unlocked their potential. First, the explosion of digital data, images, text, and video, gave models the fuel they need. Second, GPUs, originally for gaming, made training complex networks fast and affordable. Third, new algorithms and architectures, like better activation functions and smarter weight initialization, solved old problems. Innovations like convolutional and recurrent neural networks let us tackle images and sequences with ease. The convergence of big data, powerful hardware, and smarter algorithms propelled deep learning from theory to world-changing reality. That's why AI is transforming our lives today. Deep learning isn't one-size-fits-all. It's a family of specialized models. Convolutional neural networks, CNNs, excel at images, scanning for features like edges and shapes, perfect for medical imaging and self-driving cars. Recurrent neural networks, RNNs, handle sequences, remembering context for tasks like language translation and speech recognition. Transformers, with their attention mechanism, revolutionized language models, powering tools like GPT-4 that write, code, and converse. Generative adversarial networks, GANs, pit 2 networks against each other to create stunningly realistic images, art, and synthetic data. Each architecture is tailored for its domain, pushing the boundaries of what AI can do. This diversity is why deep learning adapts to so many challenges. The right architecture unlocks new possibilities in every field. Deep learning's power comes with real challenges. Training top models demands massive data, energy, and resources, concentrating power and raising environmental concerns. Neural networks are often black boxes. We see their decisions, but not always the reasoning, which is risky in medicine or finance. Bias in training data can lead to unfair, even harmful outcomes, amplifying societal inequalities. Ensuring fairness and transparency is an urgent ethical challenge, not just a technical one. Deep learning is a powerful tool, but it reflects the data and values we give it. As we advance, we must build AI that's not just smarter, but also fairer and more transparent.